Thanks for coming, folks. My name is David Wheeler. I'm an engineer at the New York Times and a longtime member of the Postgres community, although it's been a while since I've been here, and I last came to PGCon in 2015, I think. But I'm glad to be back. It's good to see you all. It's good to be seeing people in person. Today I want to talk about a project we've been working on at the New York Times, which codenamed CipherDoc. It's a searchable, encrypted JSON data store that I built on top of Postgres. So, is this actually going to work? No. I'm going to do this the old-fashioned way. So, I first want to talk briefly about kind of the principles we had for the team I joined at the Times. We wanted to, first of all, put the intentions of our users first and primary. We wanted to foster continuity across experiences in the New York Times. We have a lot of silos and a lot of groups doing a lot of different things. So we wanted to kind of increase continuity. We want to empower users with transparency and control so they know what they have and are able to manage it. One of the most important aspects is to protect the data that is entrusted to us and the document storage we want to build, and to build it together so we collaborate with the other teams to get them the functionality they need. So with this in mind, we set forward to build a centralized document management service with a number of features. Yeah, that's actually working. Nope. There we go. First, a standard accessible web API that's straightforward for engineers to use. It needs to be able to validate and enforce the schemas of the documents that it maintains. We want the data that is managed and stored by the service to be completely worthless in the event of a breach. And we need to be able to support secondary key search. So I'm going to talk about these in sequence here today. So let's start with the web API, which is built using REST. The API is a pretty straightforward, intuitive CRUD interface, nothing too fancy. This is slow. So you're able to fetch a document by an identifier, a unique identifier that's assigned to each document. It's basically a simple key value design. You have a key, an ID, you can get the document for it. It's almost boringly RESTful. So if we think about it kind of notionally, under the hood, the data schema might look something like this. We have a unique identifier that's a UUID, and then we just have a JSON blob for the document, right? So let's see what that looks like. So let's create a record with this file here. We have, I'm going to be using user as an example here because I think people can connect to that pretty well and understand what the use cases generally are. So we just have a user here whose status is enabled, has a profile with a username and their full name. So all we're going to do is post to create the record to the URL. That's the collection of users in the system, and it creates it. That's it. So note here that it returns the location with a canonical URL with the ID. Ooh, that's not double clicking. The ID that's been assigned to it, here I can point here, by the system. And that ID is also part of the head section of the document that's returned. All the heads data is maintained by the service itself, whereas the body is the actual document that the user cares about. And so we just have information here about the identifier, and it's the same that's used in the REST URL. So we're going to use that URL for the other commands we want to use against the document. So for example, we can of course fetch it by doing a get at that URL, and it just returns our copy of the document. Yeah. I wish I could, but JQ did not give me the option to do that. I'll read them where it matters. It's a good point though. So what about an update? So what we do is I'm going to do a put to the URL for this document that's just adding a location field. So to post the record or put the record, we're just using the HTTP put command to the URL, the canonical URL for it, and giving it the document that we want it to store. And there it is. It has added the location data. So, you know, what's cool? Patching is cool. So this is a RFC 7396 JSON merge patch. The idea of this patch RFC is you basically just have a subset of the document that describes the things you want to change and you omit everything else. So in this case, we have the body, profile, and location is set to null, and that means delete the location. Remember, we added it a moment ago in the put. And then we're adding an email address here, which we're setting. Yeah, I said all that. So we use the HTTP patch command to patch it, send it the document, and boom, we've got the email here. You can't see the header, but the email address is there. Hopefully that's clear. And the location has been deleted. And of course, we can use the HTTP delete command to delete the document. It returns a 204 because there's no body once we deleted it. And to make sure, we can try to fetch it again. And of course, it returns a not found error, right? So pretty straightforward, RESTful stuff. Hopefully, most of you are familiar with the idea. So as I said before, one of the important principles for our team is to protect the data that's entrusted to us. And so therefore, we have the requirement that in the event of a database breach or a dump, that any of the data that's in there is completely worthless to the breacher. So by implication, that means that you actually can't store any plain text in the database. It has to be worthless. So we adopted an encryption pattern to protect the data. We're using AEAD encryption, which is the current industry standard for best practice for symmetric encryption. It authenticates the encryption, so you can make sure that nobody has messed with and changed the data in the encryption. It uses additional data, which in our system, we use the UUID as additional data, and that way you can't swap records for different UUIDs. And the entity is fully encrypted in the database, but we're leaving the ID unencrypted. So notionally, right, we have the original users table here for our entities that had a JSON B column. We're just going to change that to a byte A column. That's the only change really to the schema we're talking about. So how do we go about encrypting the data? That seems like a significant potential undertaking, but fortunately, Google has released an open source library called TINK that kind of provides a lot of the best practices for encryption. So TINK is an open source cryptography library written by Google cryptographers and security engineers. The idea is that it has a simple and secure cryptographic APIs it provides for people to use. So it's user-centered design, so it's relatively straightforward to adopt and understand. They wanted to reduce common pitfalls like how do we format the ciphertext so we don't break things. And they emphasize careful implementation and code reviews and extensive testing for their system. So with TINK, you can safely implement the most common industry standard cryptographic tasks. And the library is widely deployed at Google, so there's a lot of real world use behind it. It supports the AEAD encryption we need and HMAC message authentication, as well as key rotation, which is one of the key features that's tricky to get right. Now, the keys that you use in TINK and a TINK keychain are rooted by a KMS. So that means you need to have a key in Amazon Key Management Service or Google Key Management Service or HashiCorp Vault or something like that, that actually encrypts your keychain, keyring, that's used by the system. It handles the formatting of the ciphertext, so we don't have to figure that out. And it has the tooling for configuring and rotating the keys within your key thing, so a key ring. So let me give a brief demo of kind of what that looks like. Here. So let's have a look at the keys. This is the key ring we have, and I'm just looking at the key ring info here. First of all, we have two keys active here. One is 1179, right? And that's using AES GCM encryption. And the other key is 3304, that's using XChaCha poly encryption. So you can actually change the algorithms over time as you add and remove keys from your key ring. Currently, 117 is the primary key, which is defined up here. So this tells you which one is primary. That's the one that's used for encryption. The other keys, any other keys in here that are enabled, and you can see these are both enabled, can be used for decryption. So this allows you to rotate in a new key, make it the primary. It starts encrypting new records. Existing records can still be decrypted with the old keys. So let's create another record here. I'm just going to post a document, right? Just like before. So note that there's the ID here, 8KXC is part of the canonical URL for it. That's actually a base 58 encoded UUID. Use base 58 to compress it, so it's a much shorter string length than your typical UUID hex representation, and it's easier to copy and paste into URLs and stuff as well. So we're actually using the UUID in the database, so that base 58 encoded version we saw was actually the same as this one, 3B55. But you can see here that we have just the UUID and then the encrypted entity here. And that's all we have in the database. Now note here that there's a prefix here, 0107. That is the ID for the key that was used to encrypt this record. So let's rotate. We're going to make key 3304 the primary key, and we'll be using it to encrypt. Now, because the keys are KMS rooted, I need to tell it what Amazon Key Management Service key to use to encrypt and manage the keychain itself, the key ring itself, excuse me. So I'm setting up a URL here for a KMS key. And so I'm going to use the keyring command, which is part of the CipherDoc service. We use promote key command and tell it to promote key 3304. I'm telling it to do it in the data encryption key configuration file that we've been using that defines all the keys, and to write it out to the same file. And I'm telling it that this is the key to use to decrypt and re-encrypt the key ring itself. So it does that. It's promoted the key. And if we look at the key ring here, I'm just selecting the key ring info. There's actually a separate bit that's the encrypted by the key ring key. It has all the keys in it. This is just informational here, for human legible. But we can see now that key 3304 is the primary key. So we've switched from 117 to 3304. So let's look at the logs for the service. It's using a file watch rule to watch the data encryption key file, and so it knows when it's been changed and can reload the key. So it knows that the new key has been promoted. So that means without restarting or anything, we can actually go ahead and use it. Of course, we can still fetch the record that we created earlier because it was created and encrypted with the old key, 117. And that's still enabled and still available for decryption. So let's update it. I'm going to just do a put to that record to create a new record. And of course, we can still fetch it, right? So that's good. Now it has been encrypted with the new key. And how do we know that? Well, previously when we looked in the database, the prefix for the record was 0107. What's there now? If we look at that record now, we can see that there's a new prefix, 01C4, and this is the new encrypted record that's using the new key. Right. So that's how we've adopted TINK to manage the encryption and the key management for the service to encrypt the documents. Now, one thing that we don't have here is we just have a JSON blob that's encrypted and a UUID. We don't actually have any schema enforcement, and we want to make sure that the documents only contain what they're allowed to contain. So to handle this, we adopted JSON schema, which is an industry standard solution for schema validation of JSON documents. So the basics are that you can use it to annotate and validate JSON of all types. It can be used to describe the data types and formats. I wonder if this button will work now. Yeah. It can also be used to generate human-readable documentation. It's actually a nice complement to OpenAPI/Swagger for those kinds of purposes. It supports composite types, and you can actually compose multiple subschemas into additional documents, almost like if you define multiple tables and you can assemble them into a document. And this makes sense if you think about a JSON schema as generally describing nested JSON objects. But it's also extensible and customizable over time. You can add additional stuff to it, and you can add your own customizable kinds of commands if you implement the parser support for it. So just to think about kind of the traditional model, if you were managing users, you might have a user table, right? And I'm going to kind of be working through this example here. And in a user table, you're going to have like maybe a status column, and you have a check constraint here to ensure that it is only enabled or disabled, and those are the only two values that are allowed to be set for the status. You might have a couple of columns for the user or the end client that actually created and last updated the record, of course, with some constraints on the size of it. Same thing for timestamps, when it was last updated and when it was created. And then we get into the profile information for the user themselves, where we have a name that's limited to a particular length. We have a username that's limited to a particular length. You can have something like an email address, and then maybe use a check constraint and a custom data type or regular expression with a check constraint, as I've done here, to ensure that it looks like an email address. Same deal for phone numbers, again with these limitations on the max size and comparing. So that's kind of how one might think through creating like a user's table in a traditional database. Now, you can do all the same kinds of things and more with the JSON schema. So a JSON schema works like this. It is itself an object that has keys and values that define what it is that it is going to validate. So I'm going to declare a schema here for a user, and it has a brief description about what that means. The type of JSON object that a user is allowed to be is an object, and that object is allowed to have certain properties. So we have, for example, the property status, which is the status of the user. And we can define here a default and an enum, and the JSON schema validation library will use this information to ensure that it is only those values, just like your check constraint does in the database. Similarly, another property here is a profile, which is actually a reference to another schema, which I'll get to in a second. And we're saying that there can be no additional properties on the object, meaning that you're only going to have the status and the profile. Now that profile, there was the $ref key that pointed to another file name, and that was profile, the profile schema. So that's as a separate, can be a separate document, separate file, in which you define that JSON object that's just for the profile information. So here we're saying the profile it's also an object. Its properties are names. Now we're getting into the user's profile, which is of type string and has a max length, just like our database table did. Similarly, username has a type of string and a max length of 64. What do I keep bumping here? And you can also have examples, which is great for documentation generation. For the email address, there's actually, in addition to the type string, let me see if I can do this without the button. JSON schema defines certain formats so you can use for additional validation. And so one of the ones that's included in it is email address. So we don't need to use the regular expression like I was using for the database example. But we can also, as in the database example, use a pattern here, a regular expression, to validate a string method, just like we could in the database with the check constraint. So that's how I might model like what a user is. And in the CypherDoc system, you can define whatever type of entity or document that you want. Now, these are all wrapped in a higher level schema, which we call entity, which may be renamed at some point. It is, if you recall from the examples we've seen before, there are two properties it has. There's the body. Oh, I keep bumping stuff, sorry. Go back. I'm just gonna use the keyboard. Which can be any one of an array of other schemas. So here I've said it can be a user or it can be an organization, right? And these are defined by other schema files. The user one we saw before, you can imagine an organization one. And as you add different types of entities, you just add them to this list. And then there's the head, which remember has kind of the metadata that's maintained only by the service itself. That references another schema. Let's take a quick look at that. One of the important facets of this head schema is that we annotate it as read-only. So that means that any client that is consuming our schema, in order to understand the structure of the documents themselves, they know that that is a read-only part and is maintained only by the service itself, and they shouldn't change it. And then we just define all the properties that are in the head section we saw before. The ID, which is a base 58 encoded UUID, the type, which is a simple string here, user or organization I have here at the bottom. These actually need to be the same as the list of any of we had in the body section previously. And so there's actually a comment here, $comment allows you to actually insert a comment that doesn't get put into documentation. So that it kind of helps you understand what you need to do there. So we have created at and updated at. As with email, there's actually a date time format that's supported by the SQL, the JSON schema standard that handles enforcement of data types, date types. And then we just have a couple of strings for created by and updated by, right? Again, with the constraints on length and what have you. So let's take a look at that. So let's try to create a new record. I'm going to post a new record here, and it fails. It actually tells me the record is invalid. Now, it doesn't give me much information, but we can look at the logs, right? So I'm going to look at the logs that are running in the service, and we can see here that it says username max length must be 8, but it's 12. I thought we wanted to allow usernames to be 64. Well, I'm going to take a quick look at this document. Yeah, okay, that's username is certainly longer than 8 characters. So inside the schema itself, we have here the max length is 8. So I have a typo. So I'm going to fix it. I'm just going to run a quick Perl replace on it to change it from 8 to 64. Take a look again. We can see now the max length is now allowed to be 64. And then in the service itself, there's a configuration file currently called entities that tells it what schemas to load. So I'm going to touch that file because the service also has a file watcher on that file and knows it needs to reload all the schemas. So if I look here, you can see, yes, in the log, it shows the models were reloaded by the service because it saw that it changed. So now we can try to post the document again, and now it successfully creates with the 12-character username right there. So that's how we have it configured for schemas, and it loads the schemas and uses it to enforce the models of the documents it manages. So as I said, one of our principles is to foster continuity, and that means making our system like the central repository, the document system of record for a lot of the teams across the New York Times. So the challenge is that we have all these entities scattered across the different parts of the organization, and how do we bring them in? We need to be able to integrate with partner teams to give them the data they need in order to be able to do the stuff they need to do for their particular business cases. So JSON schema again comes to the rescue here through the design of our current schema, which is independent of how the system itself works, but just taking advantage of JSON schema itself, is an extension schema. So an extension schema can contain one or more extensions, and an extension has this JSON schema, where we're saying basically it has to have at least one property, otherwise why have the object at all? It has an ID, which is perhaps the ID from the other team that they've used traditionally for their user or organization or whatever. There's also the @ID field, attribute, property. I always forget which term to use there. The @ID property is actually a JSON LD URL for canonical resource. So another team might have their own system in which they have users set up with some other ID and have their own REST URLs for that canonical record. So if what we have is a copy as a reference to that, this is a pointer back to the system of record for that particular entity. We also here have additional properties as allowed to be true, and that means in addition to ID and @ID, they can put in whatever other objects they want into a particular extension that fits their particular use business case. So extensions are part of the extensions top-level schema, in which we just have an enum here for the proper names are allowed to be billing, messaging, or games. Like for the billing team, the messaging team, the games team, each can have their own extension of a user object or whatever object. And then the properties that are able to be defined for this object use that extension schema we were just looking at. So that means that billing can have a key that points to an object, and the object must comply with the extension schema that we've defined. Now, in addition to using this extension schema with the ID and @ID, it could be we work with another team who has more specialized use cases, and we don't want them to just put whatever inside the object, but want some level of control. We could work on a schema perhaps that's specific to the games team, that's different and customized, and then we'd specify it as a property pointing to that schema here, rather than having it as part of this enum. So let's look at extension demo here. So here's a file with billing information for a particular user. Since I know this is dark blue, it's hard to see. We have the extensions key here as part of the user object. There's a billing key in there that points to an object that has an ID. Here it's 787E yada yada. And then they can have any other keys that they want in here. They put one in here. The product they have is home delivery, for example. So I'm going to post this record to create it. And, oh, hang on. So the object is not right. Let's take a look at the logs here. It says that extensions is not allowed in user. I forgot to add that to the schema. So we can see it's actually being enforced. So let's update the schema. I'm going to copy over a new user schema here that has this change in it. It's adding extensions top-level key to complement profile and status that we had before. And then, of course, it references the extension schema we were defining a moment ago. So I'm going to apply that, just copying it into the configuration directory the service is using, touch the configuration file for entities, and make sure it reloaded. Yeah, so the models were reloaded. So that means if I try to create it again, it now works. And you can see that in addition to the service assigning all the head information as before, it is now has the extensions object with billing and the billing ID and the product and whatever else is defined for billing. Right? Yes. Oh, okay. Right. So hang on a second here. I want to draw attention to this. Clients need to be able to look up objects by their own ID. So remember, we're building in objects from other teams and putting it in extensions would have their own IDs. So for example, the billing team might have this billing ID that's part of the record. They don't have the canonical URL canonical ID that gets generated by the service necessarily. They have existing systems that have this billing ID. So the question is, how do we find a user record with that billing ID? Now, if we look at the database again, it looks something like this. Now you note here that because the entity is encrypted and there's no plain text in here anywhere, you can't get at the billing ID. So how do we search it? Because encrypted data, of course, cannot be queried. So what do? Because encrypted data is not searchable, but we still want data to be useless, right? So we could just like stick a separate JSON object in there that has like the billing ID, or add a billing ID column or something like that. But then that becomes visible to anybody who dumps the database. So what if we did this instead? What if for particular fields that are in the object, we hash the values along the path to those fields and store those hashed values in a JSON blob instead? And we can use HMAC, so we actually have a key for this hashing, right? And associate it with the AEAD key that TINK generates, kind of pair them together as a single thing. And that way we get unique hashes for a value per key. And then we tell it what data needs to be indexed by this method and how to find it. You with me so far? So just on notionally back to this table again, kind of the data, whereas before we had an entity column, now we're going to add back a new JSON-B column, which here we're calling lookup because we're using it to look up records. It's a lookup index. And I'm putting an inverted index on this column, along with the JSON-B path ops for efficient path query execution. So this will allow us to find values within this JSON blob efficiently. So let's take a look at how the keyring here works. So this is the keyring, same as before, only remember we rotated the key. So now we're using key 3304. You can see that's the primary key there. And it uses XChaCha poly AEAD encryption, but it also specifies a hasher here. That key says hasher. It says SHA-1, right? There's also this key here, 117, it's using SHA-256 hasher. So just as we could change the AEAD encryption algorithm per key, we can change the hashing algorithm that's used for the HMAC key that's used for hashing values. And that way we can rotate them together in order to change values over time. So here's what the contents of a lookup column look like in the database for the record we created a few minutes ago, this record 5A5. You can see here the keys may be hard to make out, but it's a gobbledygook ASCII for each of the keys in the path. Excuse me. And then we have more gobbledygook ASCII for the values. So what this is that the keys are SHA-1 hashes generated by the HMAC key that's associated with the key that we're using. And they're truncated to 4 bytes. And the values themselves here are the full SHA-1 hashes. These are base 85 encoded to make it as compact as we can make it while keeping it ASCII, which is what JSON requires. I mean, text, which is what JSON requires. And it also allows us to do quotation safely because base 85 doesn't contain any quotation marks. So we got it to index this. How do we query this? How does it know what to index, and how do we query it? So how do we query it? We use SQL JSON path. Now, SQL JSON path, inspired by JSON path, is part of the SQL 2016 standard, and it's been implemented since Postgres 12. And I'm going to talk a bit about it. One of the key features is it supports placeholder values, not unlike when you're preparing a query in a database. And you can query multiple values at once in the path. So just as a brief introduction for SQL JSON path, I'm going to give you some examples comparing it to a where query. So let's say you want to find users where the profile email equals $1, which is a placeholder variable for some value. The way this works in SQL JSON path is you first select the root, which is $. That's the entire value of our JSON object. The profile key, right? We select that. And so that's the path we're selecting. Then there's this dollar open parenthesis. That is a filter expression in JSON path. And within the filter expression, the @ sign is a new variable that represents the path most recently selected. So the @ sign here is actually the object that's stored in the profile key, right? So within this filter expression, we can look at the email property of the profile object just by referencing like this and compare it to using the equality operator, $email, which is a placeholder variable that we can use in any expression and will later be replaced with a value for an email address, right? If we're comparing two things, right, where we want to know where the status for the user is enabled. Remember, status is a top-level field in our user object. And the profile.email is equal to a placeholder value. Here we're selecting the root object and then just opening the filter expression with $ parenthesis. And that then includes the entire user object in the filter. And that is represented by the @ sign variable. And then we can reference the fields individually for that. So we say where the status is equal to enabled, and the object profile.email is equal to the $ email variable again. Right? Pretty straightforward stuff, hopefully. You can also, of course, use the placeholder multiple times. So if you might want to find any user, when we have 2 email addresses we support for users, you want to find any user that has either of those email addresses. In SQL, you might say where profile.email equals $1 or the profile email 2 equals $1. Similarly, in SQL JSON path, we select the profile object, open the filter expression. The profile object is in the @ sign, and we say where its email is equal to $email or email 2 is equal to $email to compare those values. Right. So the service has a configuration for the paths that we want to index and search. So going back to our user object, we're saying, okay, we want to be able to find objects based on email address. So we have email as the key in this configuration, and then we have the SQL JSON path expression for that, in which we use a variable with the same name as the key, email. We can do the same thing to search by username or billing ID, simply by specifying billing ID is a variable name, and here's the expression to search it, and where the variable gets replaced in the expression. This also defines which fields get indexed. So we don't want to hash the entire object to store it in the JSON-B because it's only a small subset of the fields we're going to end up searching regularly. And so it would be inefficient and expensive to index the whole, like dupe the entire JSON object and index the whole thing. So we use this configuration to know we need to index the email, username, and billing ID, and nothing else in a user object. So we set up an API for searching by secondary key. Remember to get an object by its canonical URL. There's the UUID that's part of the URL. Here we're specifying a key value pair separated by a colon as just a straightforward REST API to say this is a secondary key we're looking up, and this is the key we're interested in, and this is the value. And this blog post down here goes into details about the design. So we can, for example, to search by email, we do a get at users email : hi@example.com. For users, username, for the username, we do username : the username. And similarly for billing ID, we say the billing ID is this. And so here's how internally the service works to translate that. We call get email : drummer@tyco.station. It knows from the key here that it's email, so it looks for email in its configuration, and it knows that it finds this SQL JSON path expression. So to convert that SQL JSON path expression to replacing the variable, and then it can hash it, right? So here it's applying the SHA-1 hashing to convert each of these segments, binary profile.email, into their 4-byte truncated SHA-1 representations, and then for the value, the full SHA-1 hash for the representation. And because, remember, we have two keys, one that's using SHA-1 and an existing key that's still enabled that uses SHA-256, we need to generate a second SQL JSON path expression for that. So now we have these two of them that actually are the same as this other one because it needs to be able to search for values hashed by either of the keys. So the resulting query ends up looking like this, where we're looking at the lookup column, we're using the exists operator here, and then just passing an array of all the SQL JSON paths we have generated. So how do we do the hashing? We need to be able to parse these SQL JSON paths in order to know where the keys are that need to be replaced in this thing with the truncated hashes, to replace the values that are in it, like enabled in the early example, or variable values with their hashed values. So it has to understand actual SQL JSON path syntax in order to do this correctly. Now, the CipherDoc service is written in Go, so what we chose to do, perhaps ridiculously, was to port the Postgres SQL JSON parser to Go. Over drinks later, I'll tell you how badly I did at this. But it works well enough for our use cases here, at least for now. So if we just think it through, right, we might have a function that we can pass a path string to and parameters that would be used to replace variables within that path expression. And so what it does is it parses the path to generate an abstract syntax tree. The abstract syntax tree contains the entire expression of the path as a series of objects. So then we're getting a list of all the hashes that are in our data encryption key, because remember we have 2 as in our example, but there could be more. And we figure out how many queries we're going to end up needing to generate, one for each of those hashes. And then we just iterate over those hashes and compile each of these, recompile the abstract syntax tree with that hash and the parameters to replace its variables. And simply return the queries. So the hash compile function itself just delegates to another function and passes the root node of the abstract syntax tree to get it started. And the magic happens then in the node hasher and function here, hash node. And all it does is simply switch off the type of each node in the abstract syntax tree to decide how to treat it. So if it's a string, a number, a Boolean, or a null, it's just going to return a hashed representation of that value as a new string node. If it's a key, it's going to hash the string representation of the key and then truncate that hash to 4 bytes and return that key object. If it's a variable, it's going to use the text of the node to look up the value within the parameters that are passed in, right? So this value might be email. And so within params, email is going to point to drummer@tyco.station and then hash that and return that as a string. And because SQL JSON path supports all sorts of operations and functions and stuff, we can recurse into the hash node tree based on the type. So for example, just here, we have maybe a unary operation node. So we're getting the single argument for that node and passing that to hash node to descend into all the parts and returning a new unary operation of the same type and with that now hashed argument. So remember, the lookup column can look like this with these hashed values. So let's look up by email. I'm going to use user's email :drummer@tyco.station to try to find it. And it does successfully find the record right here. You can see that email address is right here. We can do the same for billing ID, right? So I'm billing ID : the billing ID. So it knows to find the path expression for billing ID, substitute that 787 value and hash it and look it up. And sure enough, it finds the record right here. Now, of course, it shouldn't find an invalid ID. I want you to know this is actually working stuff here. It's not just mocking it all up. So when I try to search by an ID that doesn't exist, it returns no record found. So let's look up a different user. Let's look up someone by username. We created this Naomi object before, so I'm going to search by username Naomi, and it finds it. Let's change the name of this username of this user. So I'm applying a patch where I'm changing the username to Knuckles here. So we can see, yep, it patched it and changed the username to Knuckles. That's great. So if I try to find the old username, it doesn't find it. But with the new username, there it is. There's Knuckles. And I've searched by username :Knuckles. Now, just a reminder, this is what now the entire row looks like for this record in the database. We have the UID. We have the AEAD encrypted value as an entity. And the lookup, we have this hashed up JSON object that we're using for these queries. Not much to be used here for anybody who dumps database. So there are a few downsides to this approach, or trade-offs, let's say. Key rotation requires record rotation. So if I've switched in a new key and I eventually want to get rid of the old key, I have to re-encrypt any old records that have been encrypted with the old key. Schema changes don't validate existing records. So if I say I want to add a home address object to my schema and there are existing records in the home address, they're not validated by that. It's only newly updated or inserted records that would be validated. Similarly, if we add configuration for a new lookup field, if I add a new config for find by phone number with the JSON path expression, any existing records with phone numbers won't actually be indexed in that JSON-B object because the system parses the configuration of JSON paths to know what's supposed to be indexed. And of course, I've been saying like we're doing secondary key lookup for all these things, but the truth is there's no enforcement of secondary key uniqueness in the system. And it's impossible to do because you can have records hashing values with multiple hash keys, and that means that you can have the same value hashed by two different keys, which generates two hashes, which then appears to be unique to the system. Never mind a hash collision being an issue. So we plan at some point to develop a utility service. I'm just code naming Upkeeper, whose job is to like re-encrypt older records with newer keys or to re-index older records with new keys. So for the future, we want to look at implementing this Upkeeper-like service. The SQL JSON parser needs a rewrite. I hand wrote the whole thing, which is a terrible, terrible way to do it. We'd like to implement first-class TINK key integration. Right now, the way the HMAC hash key is associated with the TINK key is it's kind of bolted on the side, and there's a way through protobuf magic to actually integrate it right into TINK, but haven't been able to learn that bit yet. And we might want to look at other changes as we start to have other systems and teams use this thing. Like, should all that head stuff with like the ID and the created by and created at be its own column that's not encrypted? That's going to come down to the use cases that come up and what the trade-offs are between how much that reveals about a record versus utility we get from using it. So this is the sorts of things we can iterate on. And we're also talking about whether we can open source this service to make it more generally usable broadly by people to adopt and to use it to protect effectively through encryption their documents while still being able to find them. And that's it for my presentation. Thank you. I ran a few minutes long, but I can take questions on it. Oh, I guess we have lunch coming up, so there's probably no rush. Yeah.
I was trying to understand what is the functionality that you get with Postgres in the picture. This seems to be like a use case for a document store.
We're basically using Postgres as a document store. And JSON-B is actually a great choice for that in general, right? But we also get the advantage of being able to use standardized features like SQL JSON path to do the search. And also, Postgres is, well, SQLite's done some stuff with SQL JSON path too, but Postgres is the one I know that has the most robust library, so I was able to actually to port it to Go in order to be able to support the hashing bits. But that's a valid question, and lots of people at work ask me, why are you making a database outside the database? You're not using it as a relational database. I'm like, I know, I'm cheating. Yeah.
Is there anything new you see coming in the next version that would have made your work easier? Because there was a lot of JSON path stuff that was not committed, and now it's in the next release.
I'm sorry, can you ask that again?
So in the past release, there was a lot of new JSON functionality
Yes.
that didn't make it and had to be reverted, and is now coming in the next version.
Oh, of Postgres.
Look forward to see what would have made your work a bit easier.
It means that I'd like to figure out how to generate the parser using a grammar as opposed to the handwritten stuff I've done now, and that'd make it much easier to adapt whatever changes come to Postgres stuff. So for example, with SQL JSON path, you have to use double quotation marks for the path segments, and JSON path that you probably use in JavaScript or Python or whatever, use brackets. And I know that the work has been done in Postgres to support both. So it'd certainly be something that could be integrated into the parser if it wasn't this like 3,000 line monstrosity I handwrote. But it's also true that we only will ever be able to support a strict subset. But because what we're doing is comparing hashes, there's only direct equivalence comparison we can do. So the only operators that really matter are equals, not equals, and not. And like greater than, less than, all this other stuff, all the functions, no use for them for this particular use case. So yeah, for additional syntax and the sugar for that, I could definitely see that being useful and more transparent to people. Yeah. Yeah. So TINK provides all that stuff already. And so you can use those libraries. I implemented the keyring utility you saw here as its own sub-package within the repository, so it could be separated out if we wanted in order to get that utility and the hash key configuration mapping with it. But as I said, I'd like to make it better integrated with TINK overall. I mean, it's doing the right thing in terms of protecting the HMAC key, just like the AEAD key, using the KMS rooted key to encrypt it. But it's, as I said, kind of bolted on the side. But yeah, I tried to factor things into their own reasonable packages. Like the SQL JSON path is its own library. Other questions? Yes, sir. Yeah, do users care about the UUID or is it all about lookups? That's an interesting question. What we decided internally at the Times is that we wanted that to be purely for internal use. Other teams would use it, but like if we actually use this to represent end users, we probably would never show it to them because they have existing identifiers, which we would be expressed through the extensions mechanism. But I imagine that's really going to come down to the use case. No, the UUID never changes. I originally was designing it so like, oh, when the key rotates, it'll generate new IDs, and that just seemed really, really painful. So I talked to our data compliance officer. I said, can I get away with just having the UUID be the only thing that's in plain text in the database? He's like, yeah, that's fine. So I was like, thank God. Because the rotation and the chances of collision, and then if you do have a collision, how do you deal with it? You have to generate a new key. It was just painful to think about. And the whole thing goes away by not ever changing the UUID. Yeah.
I didn't quite understand your how the secondary indexes are mediated. You had a slide there where you showed that what's there in the database is just key and the ciphertext value.
Yes.
But then the secondary indexes are
Say the second part again.
So your secondary indexes on the fields, the various fields of interest to you.
Yes.
So that is not stored in the Postgres database or what?
Those are the bits that get extracted from the document, just those keys, right? There's a JSON path parser that understands the JSON path configuration and can just pull out those bits that have to be indexed. And that's what it hashes and stores in the database in that JSON B blob as hashed objects. So we're not storing the original value. That email address was not in the database as that email address.
So your database does have only the ciphertext values, but then if you have like 3 or 4 fields for which you have the secondary indexes, does your database maintain the secondary indexes for them or not?
Oh, the secondary index is like in the keys in the lookup object?
Yeah, whatever, like email and username.
No. All it does for indexing that JSON B blob, in order to enable those lookups, it just uses the inverted index, the GIN index, which indexes all the paths that are present in the JSON object. That's part of why we're only currently indexing just the fields we're interested in searching, because if it indexed the whole object, it would be really slow, right? Because if you give it a whole object, the GIN index will index the whole thing. We are using here the JSON path ops operator group class, I can't remember, for GIN, and that means it's actually more compact and only supports a subset of index searches with JSON stuff, but it supports SQL JSON path as long as you don't use wildcards. So that makes it the whole thing relatively compact. It's still an inverted index. It's still going to be producing like 6 rows per record, right, in that index. But it's much more compact than it would be if it had to support things like wildcards to descend through the whole tree, because we have the JSON schema that defines everything to be in the object. We don't need the wildcards. We know what things are allowed to be and what they're not. Yeah. That's great. I love questions. Any others? Any more? Thanks for coming, everybody.